Evening session, we have two plenary talks. First by Professor Murthy, and then we have arranged a special lecture by Professor Sathe on life and works of Sri Ramanujan, late Sri Ramanujan. So Professor Murthy, it's my pleasure to introduce him. He is known to all of us. He is a frequent visitor to India, and ever since he was a postdoctoral fellow, he started coming to India very often, and I think I see him much more often than many of my colleagues here in all conferences and workshops. He has guided a lot of students from India, postdoctoral fellows, PhD students, master students, and I am not able to keep up with the number of books that he has written, maybe about a dozen so far. Yeah. So, and guided more than 40 students, masters and PhD students. And also he is a professor of philosophy in his university. And right now he is a chairman, so it's a very difficult to fathom how he arranged or managed all these things with all his travels around India. It's a pleasure to have him here again, and today he will speak on measurement, mathematics, and information technology.
Thank you very much. Thank you, friends, and thank you, Ramanujan Mathematical Society, for inviting me to speak. So I want to share with you some ideas concerning measurement and how mathematics and information technology have changed the course of our life. Hopefully this talk will give you added ammunition to perhaps convince the higher-ups to fund pure mathematics. So let me begin by a simple question. Can we measure everything? Well, there's a famous quotation by Einstein which says that not everything that can be counted counts, and not everything that counts can be counted. So I would like to impress upon you that this is a very profound quote which perhaps guides the message of this lecture. Even though we may not be able to count certain things, the attempt to understand, some understanding emerges by the attempt to measure things. Now here's a quotation from an article from the New York Times which has some relevance to a point that was made by Professor Kulkarni in the lecture this morning concerning ontological understanding. With the measurement system all but finalized, why are controversies over measurement still surfacing? Why are we still stymied when trying to measure intelligence, schools, welfare, and happiness? This is a quotation from the New York Times in October 2011. Then the article goes on to say that there are two ways of measurement. One is the ontic way, and the other is the ontological way. So what are these two methods? The ontic way is what we're all familiar with, measuring things according to a scale, and it is a mathematical approach. The ontological way is more philosophical, and we understand through inquiry, reflection, and meditation. The dangers of confusing these two methods is disastrous. Here is the case of Francis Galton. Here it is. And here is what Wikipedia has to say about him. He was an English Victorian, progressive polymath, psychologist, anthropologist, eugenicist, tropical explorer, geographer, inventor, meteorologist, protogeneticist, psychometrician, and statistician. That he was knighted in 1909. He was the creator of eugenics. Inspired by Darwin's 1859 theory of evolution, Galton proposed a theory of how to create a master race by measuring intelligence of races. In his 1869 book called Hereditary Genius, he posited that human intelligence was inherited directly and diluted by poor breeding. He goes on to say the natural ability of which this book treats is such a modern, as modern a European possesses a much greater average than men of lower races. There's a straight line that can be drawn between Galton's method of measuring intelligence, particular views of master race and genocide. Dalton's view led to horrible, led to the horrible idea. And there's a nice book that was just written maybe a month or two ago called How to Fly a Horse, which I would recommend reading, in which the author traces the evolution of these ideas to how IQ was administered in the United States, and there's documentary evidence now to show that the thing was all dead wrong, because the people that were classified as backward or of low IQ went on to win Nobel Prizes. So there must be something wrong with how you're measuring intelligence. First, before measuring it, I guess one has to define it. And you still don't know how to define it. So we have to know what can be measured and what cannot. Everyday uses of measurement, well, we measure time, that's where we show up coordinating daily activities. By measuring temperature, we dress appropriately. By measuring cost, we shop for the best deal. By measuring wind speeds and atmosphere currents, we prepare for natural disasters. And by measuring distance, we can plan and travel accordingly. These are all the object uses of measurement, and all of them are invaluable in our daily life. These measurements have continued to have a profound effect, of course, on civilization. But they all need, for their usage, some knowledge of numbers. This necessity of civilization is responsible for the evolution of numbers, and therefore the evolution of mathematics. However, there are many things that can be measured that in the object. This is by using numbers. Now, the first documentary or archaeological evidence of the decimal system actually occurs in India. Here you can see the number 273 on a temple inscription dedicated to Vishnu in Gwalior, built in 876 AD. I'll show you a few more of these slides in a second. Many civilizations have a number system to count. Where does our decimal system come from? Well, from India. More precisely, the decimal system goes back 1500 years to central India. In the 7th century AD, Brahmagupta wrote the first book describing the rules of arithmetic using zero. Interestingly enough, in the same book, there is a discussion of infinity as well. So both infinity and zero as mathematical concepts seem to have origins in the hands. Well, the number 270, as I outlined, if you can read it, I'll read it for you a bit. The inscription of the temple says, the whole town gave to this temple, which Allah, the son of Vallabhata, had caused to be built, a piece of land 270 hastas in length. That's the inscription on the outside of the Vishnu Temple. This is where the temple is, Gwalior. The rock inscriptions are part of that temple. Now, the Chinese and Babylonian civilizations had a place value in the number system as well, but it was the Indians who treated zero as a number and tried to work with it as if you work with a number. This morning we were talking about abstraction, or actually yesterday I was talking about abstraction, and I suppose that you can't get more abstract than this. The origins of zero can be traced back to early Hinduism, Buddhism, and Jainism, where the concept of nothingness as a philosophical concept equated with nirvana, or the transcendental state, and so that philosophical basis somehow led to the mathematical symbology. The Vishnu Temple here, we can see it, this is how it looks, and this is the entrance to the main idol, and there's the main idol. The face was defaced by invaders in the 15th century. Some more numbers on the temple walls. Here is the number 933, and it says, this inscription says, Om Adoration of Vishnu in the year 933 on the second day of the bright half of the month of Magha. What's that name? One more. The number 187 appears in the flower garden. So these are the numbers that appear on the inscription. So the evolution of the system can be traced to this chart, the Brahmi symbols in the first century. Here, the Gwalior symbols that we were just seeing on the temple walls were these. And then, of course, the modern number system is the Dürer system that we're using here today. But you
Arabic
can,
is not in the other order.
pardon me?
Arabic is not in the other order.
Pardon me?
Right to left or
numbers
left to
are
right?
written from left to
Right,
right
right.
rather than from right to left.
Yeah.
That is,
No, this is, yeah, I think, I don't know, I think is it in the wrong order? Well, that's what they call it. It doesn't mean that they're Arabic. Notice the similarity between the Gwalior system and our modern system of numerals. So the migration of the number system, here familiar operations of numbers were discussed in great detail by Ramanujan in the classical work Ramanujan Mathematical. The number system then went to the Middle East through the traders in the 8th century. And then in 825, Al-Khwarizmi wrote a book called On the Calculation of Hindu numerals. The modern word algorithm comes from Al-Khwarizmi's name. In 1202, Fibonacci took the number system from the Arabs and introduced it to Europe. It was not widely used until 1482 when printing came into Europe. So where's, look at the gap, you've got 600 AD, Brahmagupta's work, which was already indicative of the fact that the number systems were current in the Indian society, but they didn't gain currency until 1482. These events animated the development, in my view, of modern mathematics. Okay. So what is mathematics? And here's a nice quotation. Mathematics is one of the essential emanations of the human spirit, thing to be valued in and for itself, like art or poetry. This also dominates the theme of my lecture here. Mathematics as a language of science was described and glorified by Galileo. Nature's great book is written in the language of mathematics, Galileo said, and Gauss is on record as saying that mathematics is the queen of science and number theory is the queen of mathematics. I hope everyone got that. Now, the physicists are all, fond of saying that it's amazing that mathematics does a good job of describing the physical universe. And this is the quotation of Wigner, who said, the miracle of the appropriateness of the language of mathematics in the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. To this I can also add a quotation of John von Neumann, who also was interested in artificial intelligence in the context of his book on the brain of the computer, says that mathematics seems to be a shadow of the language of the brain. He's trying to figure out what the language of the brain is, and he seems to say that mathematics is a shadow of the language of the brain. So mathematics is now being applied to diverse fields of learning, never imagined with remarkable success, and I want to discuss those applications in this talk. So we'll highlight some examples of this phenomenon. What are the examples? Well, I'll just take three. We'll discuss the mathematics behind GPS, Google, and gamma knife radio surgery. The first one deals with what is position. The second one deals with what is important. And the third one deals with what is a shape. So let me begin with a philosophical question. Who am I? This is the fundamental existential question, ontological in its dimension, of course. Belongs to the realm of philosophy. Now, GPS is concerned with the question, where am I, not what, who am I? But not as a philosophical question, but actually a question in geography. So what is my geographical position? That's GPS. So how do you go? Well, here are two cartoons I just thought I'd throw in. Yesterday I discovered that I'm a cartoon character. I was up all night trying to figure out whether I'm the lines or the spaces in between. I think this is very profound. We identify with what we read. Here's this guy who says, who am I? I'm the guy who reads I bet you can't read all this stuff here at the bottom, but it says, I'm the guy who reads the New York Times, the Wall Street Journal, the Post, Newsweek, Time, and Business Week. That's what I am. So, identification is what we read and what we acquire as information. So let's see, how is the world without GPS? Well, I don't know if you can read this cartoon. In 1/4 nautical mile, you have reached your destination, and here's, I guess, Columbus. Thank you, Senor. You see, gents, I just put in East India, and here we are. And Bugs Bunny could use GPS because it's always taking that wrong turn at Albuquerque. So I knew I should have taken that left turn at Albuquerque. So the world with GPS if you know where you are, right? I told you not to buy that GPS on eBay, but you listen to me. Oh. And then modern day offices are getting bigger and bigger and using the GPS to navigate through them. And here's one of my favorite ones. Why does the chicken cross the road to see GPS recalculate? Okay, so let me give a quick description of how GPS works. It works on satellites, of course. Each satellite sends signals indicating its position and time. So there's a satellite. And then you have a GPS receiver either in your car or wherever. And that GPS receiver receives that information from the satellite. So each satellite on the network sends a signal indicating its position and time. And that determines, so since you know the satellite's position, and you know the time, you know the radial distance because you know the signals travel at the speed of light. So your position is determined by a sphere. A radial a sphere of radius, that distance that you already have, the center being on the satellite. So you're on the surface of a particular sphere, but you don't know what's your point. So you need a second satellite in order to do that. So since signals travel at the speed of light, and determine the radial distance, and then figure out where it is on the sphere. Many think that the receivers transmit information, but it's not true, but it's only receiving information. And then the receiver uses basic mathematics to determine its position. So let me give you the idea here. So if the receiver is r units away from satellite A, the receiver lies on a sphere radius r, centered at A. Then you take a second satellite, positioned in another place, which you already know, and the intersection of these two spheres determines a circle. So now, instead of a sphere of possibilities of where you are, it's now a circle of possibilities of where you are. Now you take a third satellite and you do it one more time, and then the intersection of two circles is going to be 2 points. One of the solutions is useless, and the other one is where you are. That's how it works. So you need a minimum of 3 satellites to get GPS to work. So here are a bunch of satellites in orbit, but I animated in this fashion. Satellites are not moving; they're geostationary, right? They're moving with the thing. So you can see that at any given time here, this animation shows 24 satellites with 4 satellites in each of 6 orbits, and this multiplicity of satellites ensures redundancy to ensure accuracy. You don't, as I said, you only need 3. So the mathematics of GPS is here's how it is. I just explained that you have, for example, 2 spheres determines a circle, the intersection determines a circle, and then 3 spheres determines 2 points, of which one of them is not relevant. Okay, so equations for spheres. Well, we all know how to write down equations for spheres. You have in Euclidean coordinates a receiver at x, y, z, which is what you're trying to determine the position. And you know the first satellite is an A1, B1, C1, which is known. And so you write down the equations for that sphere. So you go take down the second satellite and you write down another equation for the sphere. And you do a third one. you got three equations and three unknowns. So it's a quadratic equation, therefore there are two solutions. So that's basically linear algebra, and you end up getting, so you do that. You eliminate, and you end up getting a bunch of linear equations. You have a little chip in the receiver that calculates, that does the matrix conversion, and solves it. And that's your position. That's it. GPS works on basic linear algebra and very, very rudimentary spherical geometry. That's it. But you needed the pure mathematics behind. Of course, the technology of satellites is a 21st, 20th century thing, but you needed the mathematics there in place in order to get this point. So let's discuss Google now. Google has become indispensable, that many don't realize that non-trivial mathematics is really behind its work. The central idea comes from a theorem of Frobenius and Perron, dealing with Markov chains. So here's Frobenius, and here's Perron. Same Perron, by the way, Perron's formula in analytic number theory, Oscar Perron, who lived to a ripe old age. You can see he seems to have been a mathematician par excellence. Anyway, Frobenius and Perron did some wonderful work in linear algebra, which is behind Google. And then that's what we need to know a little bit about Markov chains, which of course underlying theorem modeling of the Google algorithm. So these are the three mathematicians that are responsible for this. Before I describe it, let me just give you a bunch of cartoons. They're encyclopedias, actually. They're early form of Google. These days, people don't read books, right? They don't even use books. Now that our university has moved into summer hours, the library closes at 4 o'clock for the afternoon. And if you have to use the library at 4:05, you're out of luck. So it's very important to have some access to books. I'm stuck. Check it out on Google. You stumped me with that question. I think there's something you need to Google. Just go to www.criticalthinking.com and click on answers. Or here, look at this thing. Look at that one. Now, what the dangers of using websites for your information is that could be costly. So here's the web page actually. This is, I'm not making this up, this is actually the web page. Now, as you can see, one of the formulas is right, and the other is dead wrong. Now, if that was right, there would be no subject called algebra geometry. Metric mishap causes loss of Mars orbiter. On September 30th, 1999, NASA lost $1 million orbiter. I think it's a $200 million orbiter. So there's the orbiter. So here's the report. $125 million Mars orbiter was lost because of a math error. One of the teams was using English units of measurement, and the other team was using the conventional metric system, and one person forgot to convert. So the fact is what happened. And still Americans use the British system. So here's the article that talks about the mismatch, the unit mismatch between two teams. Okay, the limitations of Google. I've spent my entire life searching for meaning. My dad says if it's not on Google, you probably won't find it. Now, I want you to really keep these cartoons in mind, because it does show you the limitations of Google. And you have to understand that if we're going to push this forward, because somehow Google has replaced the library, and that's a dangerous thing. And Google is also, there's commercial interests behind Google, so you can't really trust the information. So, the web at a glance. the query, user punches in a query, and the query goes to the search engine. The search engine has a repository of document IDs, and the document IDs are collected regularly every 5 minutes. The crawler robot kind of goes to the thing and collects all the web pages. Every web page is photographed every 5 minutes or something like this, and keeps all these indices together intact. So this stuff goes on all the time. But when you punch in your keyword that you're trying to find websites related to that keyword, those search results are taken, ranked, and then spit out. That's what Google does. So it's just, instead of just dumping all the results of the search engine, it ranks the results in order of importance, or what it thinks is important. I'll come to that in a second. So this part of the thing is independent of the query, and this other part is dependent on the person's query, and it's called a page rank column. So describe that. The web is a directed graph, so let me try to explain how to use graph theory to understand the World Wide Web. The edges are the links coming into the page and going out of the page. So here's your typical web graph. The graph is more than 10 billion words in this way in a second. Page rank algorithm was discovered by these Google boys, Sergey Brin and Larry Page. Apparently there were 2 PhD students at Stanford, and they were in a class, linear algebra class, where the Perron-Frobenius theorem was being discussed. And they decided that this could easily be applied to search engines, and then immediately left the class and never returned. So they PhD dropouts actually. So, page rank axiom is basically the idea that a web page is important if it is pointed to by other important web pages. That's their definition of important. It looks circular, but we'll see in a second that we can be formulated in matrix terms. And it was patented in 2001. So Google is not that old. So here's an example of a bunch of websites. But now we have ranked them. And you can see that website C seems to be ranked higher than these websites because an important website is pointing to them. So C has a rank higher than E because even though there are fewer links to C, but the one link to C comes from an important page. So how do you kind of put this here? The popularity context, first important thing to understand is that the rank results are being calculated by popularity. So formulated mathematically, you take a graph, and use, let's say, the importance of a particular website J. We'll call it the rank of the page. So a page is important if other important pages are pointing to it. So we will formulate that by saying the rank of the website K is determined by the sum of the ranks of the web pages pointing to it, and each page J, the importance of that page will be determined by the out degree of that particular vertex. So here we see immediately, as mathematicians, we see immediately that this equation of importance or rank of the page is being formulated in matrix terms. So matrix multiplication, of course, here's how you multiply matrices. The word matrix was coined by Hermann Grossman, who was actually a Sanskrit scholar, and the word matrix comes from the Sanskrit word matra, which is the word for mother. Matra being a poem. It was coined by Hermann Grossman, who also was the first person to have translated the Rig Veda into German. So I think the first person to translate the Rig Veda into any non-Indian language. Never held a patent. He's not a university. So the creator of linear algebra was not